Hello, welcome to the midterm demo video for C.R.O.M.A, which stands for Color Harmonization from Skin Tone Recognition with Optical Monitoring for Adaptive Lighting in Entry-Level Photography.
Our team consists of myself, Matt Cope, Juanita Solania Romero, Juan Trochinsky, and Nikul Patel.
As a reminder, this is our specifications table. As you can see, it is broken up by each subsystem. And our three key demonstrables for the project are in white boxes highlighted with yellow. The following is an overview of the subsystems of the project. This is the high-level project design layout. As you can see here, the ICU is placed in front of the person when it is centered onto their face, and we have 3 light panels surrounding the subject. This is the optical design for the image capture unit. Now on the left we can see a lens simulation done in Zemax, where we see 4 lenses: a 3-inch in diameter plano-convex lens, a 2-inch plano-concave lens, and a 1-inch achromatic doublet, which is 2 lenses cemented together to reduce chromatic aberrations. Now on the right is the housing for the lenses to ensure that no light other than that coming from the optical path is on the sensor, which we will see why it is important later. As you can also see, the lens holders are modular, so they will be able to move individually from each other to ensure that the field of view is consistent throughout any working distance.
Our software is designed to process and classify skin tones in real time by leveraging multiple Python scripts and libraries like OpenCV, face recognition, and NumPy. A Raspberry Pi runs the software using a Pi camera module for image capture and MQTT for seamless communication with the lighting system. The dataset we use significantly reduced the time needed to train by providing a diverse set of labeled skin tone images. To ensure accuracy, we standardized image sizes with my resize images script, extracted RGB values from faces with my model training script, and used my facial recognition script to detect and classify live skin tones against the dataset. This system allows for real-time adjustments to the lighting setup based on detected skin tones, optimizing illuminations for diverse subjects. This software block diagram illustrates a real-time process of detecting a face, analyzing skin tone, and adjusting lighting accordingly. This system begins by capturing an image when a face is detected. OpenCV then extracts RGB values from the forehead region and compares them to our dataset. Once the best lighting setting is computed, the adjustments are wirelessly transmitted via MQTT to the ESP32 microcontrollers, which control the LED panel in each light box. This seamless communication ensures lighting adapts dynamically based on our project's skin tones. The dataset processing and model training stage is crucial for ensuring our machine learning model accurately classifies skin tones. To maintain consistency, I first standardize all images using my resize images script to uniformly format them. Then, my model training script extracts RGB values from the forehead region of each subject in Google's Monk Skin Tone example dataset and stores them in our Monk Skin Tone CSV file. This dataset contains around 6,000 labeled RGB values, saving us significant time by providing pre-labeled skin tone samples, allowing our models to be trained efficiently while requiring manual data collection. This structured dataset ensures real-time performance and improves the accuracy of skin tone classification on the Raspberry Pi. Our real-time facial recognition system successfully detects and classifies skin tones using OpenCV. The facial recognition script processes live camera feeds identifying faces and extracting RGB values from the forehead region for accurate skin tone classification. These values are then compared against the Monk Skin Tone CSV dataset, allowing the system to determine the closest match. Importantly, the test subjects we used in our demo are not included in the training dataset, demonstrating the model's ability to generalize across different individuals. By dynamically assigning skin tones labels, this system enables precise lighting adjustments, improving image quality across diverse complexions.
To properly light our subject, we're utilizing this fill light LED panel system, where our LEDs are being powered by a 24-volt power supply, while a regulator helps step down that voltage to 3.3 volts to power our microcontroller, which is the ESP32. The ESP32 then sends its data through IRLZ44N MOSFET transistors, which help send signals to our PWM LED system, as our system utilizes 5-channel RGB CCT LED lights compared to ARGB LEDs that are typically used with the program that is flashed onto our ESP32 chip called WLED.
While our final product will measure approximately 9 by 9 inches and comprise of 96 LEDs, for this demo we've built a smaller prototype with only 30. The LEDs are running at 24 volts to minimize power drop-off at lower voltages, and we're running with a pulse width modulation of approximately 39 kilohertz to ensure no flicker in any photos or video. With these calculations, we show we do hit many of our originally stated marketing requirements, including keeping the maximum power limited to under 48 watts. We've calculated the maximum light output with all 5 channels operating at the same time to be a total of 2,000 lumens, much more than our initial estimates. This slide shows our initial specifications for the project, and then our calculated values once we've determined all of our parts and our design. As you can see, we far outstrip just about all of our expectations, and including the color temperature range, the color rendering index, and specifically our R9 value, which is important when looking at human skin tones, as that does determine how much we're seeing light reflected off of the reflectance of human blood, an important metric for making sure that photos look realistic to life.
We will now demonstrate the project's progress. This is the ICU's testing setup. As you can see here, the lenses are within 30 centimeters of each other as specified by the table seen previously, and we can see that our working distance is about 8.5 feet away to ensure a proper field of view. So these are some of the pictures taken during the ICU's testing. As you can see here, the pictures of the actual person, the light and the image quality is much clearer. Now that is because lighting conditions were more favorable. The room was completely dark and the only light was shining onto the subject themselves. Now, for the other pictures while testing and throughout testing in general, the lighting conditions have not been as favorable, as there's light coming in from outside of the optical path, which means it's coming in from outside of the lenses themselves, which causes the sensor to be oversaturated with light, and it reduces the quality of image. Now, that should be fixed with the housing design that we have. It is meant to be completely dark within the housing, and the only opening is through that first collimating lens. But as you can see, the field of view is very consistent. The average face is less than 20 centimeters, and we're looking at specific points in the face to determine the skin tone. Now, we can see by the rectangle made by white paper, that is a 40 by 30 rectangle. And the pink box inside is a 25 by 25 square. So as you can see, the field of view is more than 25 in both the horizontal and vertical directions, following the specification for the field of view as per our table.
Okay, so what we're going to demo is our machine learning model. We have Luana here, and what we're going to do is set the camera to her face, and it's going to detect what her skin tone complexion is. And then right here, we're going to keep track is to see where it's going. Is it going to be consistent, or it's going to fluctuate in color detection? So let's go ahead and run the script. You can see a window pops up, showing her face. I'm just going to grab a couple of images at a time and analyze them. So far it's being pretty consistent. Then I'll go ahead and stop it. So then, as you can see in the frames that we got, it first classified her as a monk 6 and a monk 5, 5, 5. Then it started to fluctuate out to a monk 9. So, and the one I was speaking prior to this was saying that she was a monk 5 or 4 or 5, if I'm not mistaken. So far, our system is pretty good. As you can tell from our demo video on the last slide, our trained model performed well, achieving an 83% accuracy rate with only 2 minor misclassification. It consistently classified diverse skin tones, demonstrating strong generalization across different individuals. However, one issue we observed was that after extended use, some subjects began to be misclassified. I currently suspect this is due to insufficient variance in our dataset, which may limit the model's ability to differentiate between closely related skin tones and varying lighting conditions. Moving forward, we'll refine the dataset to include more diverse lighting scenarios and improve overall model robustness.
As you can see here, the 24-volt power supply is currently going directly into the LED light panel. Currently, we haven't used a step-down regulator at the moment to power the ESP32 dev board, as it's being powered by its own USB power source. The data pins from ESP32 are going to the MOSFETs to the left here, where the respective wires are being sent to each of the 5 channels of the LED panel, to red, blue, green, warm white, and cool white.
All right, this is our prototype of our light panel. We've got our LED strips, our RGB CCT strips mounted to a piece of glass for its non-conductive and pretty good at dissipating heat. We have our ESP32, which has been flashed with WLED, as well as our analog LED control circuit set up. From here, I've got, for the purposes of this demo, it connected to WLED directly because it's broadcasting its own Wi-Fi access point. So with this, I am able to turn on the LEDs, and we have control over each of the 3 channels. Each of the total of 5 channels. We can do the red, green, and blue, as well as adjust from just a super warm white, like 2700 Kelvin, to a very cool daylight white, around 6500 Kelvin. Additionally, WLED gives us the option to do presets, which is how the Raspberry Pi is going to be communicating. It'll make the decision with the Monk skin tone test, and then it'll select one of our presets. These can be customized for the eventual end customer, but for now we've just got a couple of individual ones set up. As you can see, those switch pretty quickly, and that has not had any issues with communication so far. It's been successful testing.
We will now demonstrate our 3 key specifications as per the table shown earlier and discuss the testing trials.
Here we summarize our full testing of switching to the correct prototypes. While we weren't able to get the full system up and running, we were able to test some commands, and we managed to get 100% accuracy on checking which preset, making sure the LED panel actually put out the preset that it was told to do. Even when we were controlling multiple channels, including the cool white, the warm white, and our full RGB spectrum, the panel nailed every single one of them.
This is a demonstration of the field of view specification, which is a vertical of 25 centimeters to ensure that it covers a human face fully. And as you can see, this is our lens setup here with our 4 lenses, the camera, which is right here. This is our subject about 7 feet away, and this is our image. As you can see, There's still some fuzziness in the image, but it is pretty clear. You can see what's on there. It's just that because the system is open, even this monitor right here, the lights back there, and the lights shining towards the subject are going to interfere. So once we have an enclosed ICU, all of these problems should be significantly reduced and we should have a much clearer image. But even with all the issues that we're facing, the field of view is exactly where we want it to. It's actually much larger. As I mentioned before, this white paper is 40 by 30 centimeters. Okay, the subject has not moved, but I have adjusted the lenses slightly. Any small movement, even vibrations from the table, do adjust it. And because of their varying distances, I'm not able to align it on this optical table by screwing it in, so they are just free floating a bit. But even then, we can see that the field of view still looks really good. It's still fully encompassing that white paper. We are fully making sure that the 25 by 25 field of view per our specs is being satisfied. Okay, this is our last test run. For the demonstration, I have moved our subject about a foot back, so instead of about 7 feet away, we're about now 8 feet away. So the lenses, of course, have been adjusted accordingly to be able to keep that in focus, and we can see that our field of view is now even bigger. We can fully see the piece of paper and the wood that's behind it. And what's really interesting is that we're able to get in focus just a couple of areas, but other areas are out of focus. And I believe that's because since our lenses are free floating, that the angles in them aren't perfectly parallel to each other. Instead, they're slightly turned, which is causing these slight shifts in focus. But again, once the housing is actually printed, we'll be able to further conduct tests that are much more true to our finalized product. And since the design is already done, the only thing left is to print it. The C.H.R.O.M.A team thanks you for your time and consideration, and we hope that you enjoyed our presentation.